everybody, welcome to my class. Today I am going to deal with Hooke's law in elasticity.
Before we proceed into the video, please subscribe to our channel and hit the bell notification icon to get further updates from our channel RBS Mathematics.
So today's class is based on Hooke's law. In the 17th century, physicist Robert Hooke discovered that for part of the deformation of a springs, the extension of the spring is proportional to the force used to deform it. And this relation we know as Hooke's law. So let me explain you Hooke's law using some examples here. So let's consider an example of a spring. So this is a spring, for example, and it's on a ground. Now, if you apply a force over here, then a spring will shrink, for example, up to here, all right? And then its size is like now this. You can say it is like this after being compressed. So when it is compressed by any force, the opposite thrust will act on this spring during the condition, during the state when it is compressed. So you can say that the original length of the spring as, here it is L, for example, then it is compressed by delta N, delta L. Okay, so this will be called the compression. So here, as we further increase the force, it will be further compressed down, and hence the amount of thrust equal to the force applied, that is called the deforming force. This is the external force applied, will be equal to this thrust. So in this case, you can say that the force, that is the due to which the thrust has been developed here, is, according to Hooke's law, is proportional to delta X, delta L. Okay. And similarly, let's suppose that a string is hanging on a ceiling, for example, or any hanger over here, and its original length is L in this case. And at that point, if you attach any sort of weight over here, so any sort of object over here of mass M, then obviously this of force equivalent to mg, that is called weight of this object, will cause the extension in this string. Then in that case, instead of the compression, your string will go further like this till here due to this weight, and hence your position for this weight will be like this, and weight for this is acting vertically downward with value mass times acceleration due to gravity. And here we take g value as 10 meter per square second. And because of this weight, that is as external force, a tension will be, a tension equivalent to this force W will be developed here in opposite to this force T. So that we can say that in this case, W is equal to T, and according to the Hooke's law is proportional to the extension, means up to here it has original length, but from here up to down here it has some extension. We can call it as delta L, that is the change in length, and is proportional to delta L in this case. So we can see that even if it is compressed or when it is extended, in both the cases, there will be a force developed. In compression case, there will be a thrust, and in the extension case, there will be a tension opposite to the weight. For example, here will be developed, and this force will be directly proportional to the change in the extension, and here in this case, it is directly proportional to the compression. So here we assume that the spring has weight itself 0, or we can call it as light spring. In both the cases, you can see that here in this case, F is external force, which caused the deformation in the shape and size of this spring. So F is also called, F as an external force is also called deforming force. And due to this force, there is rise of thrust opposite to the force or equal to the force F. And therefore, we can say that in this case, the state of the body is in equilibrium. All right, and same thing applies over here. So here W and T both balance each other. Therefore, here in this case, there is a condition of equilibrium of these two forces. Therefore, we can say that W equals to T, and according to the Hooke's law, it is Hooke's law states that tension is directly proportional to the, here you can say extension, and here you can say it is compression. And here in this case, we have seen that vertically upright here, and it is vertically down here. But the Hooke's law also applies in the case if your extreme spring position is like this, about this position. If you apply an external force F, that is called the deforming force. So it will be compressed like up to here, and there will be some extension. So we call it delta L or X, or it depends that how you denote it. And in this case also, it is found that, and due to this force, there will be a thrust opposite to this force F. And in this case also, it is found that T as directly proportional to the extension, or we can say here compression in the string. And similar thing you can do over here. Instead of compressing, you can extend this. Then in that case, what happens? The length of a spring will increase up to some extent. Later we'll call it elastic limit. And then here in this case, this amount of the length is the increase in length. This is called the extension, or we can denote this by delta L. Later we'll denote this by delta X. So here delta L. At this time we have been denoting by delta L. And in this case, because of any force, if you apply towards this direction, there will be a tension developed in the string opposite to F. And in this equilibrium state, you can say that T is again proportional to delta L. That is extension in this string that Hooke's law states here. It can be used for a range of applications, from inflating balloons for a birthday party to calculating the amount of sway in a skyscraper in high winds. So now, for example, let's suppose this is a light elastic spring, and here this is an object of mass m, for example. Then definitely its weight is going to be W equals to mg, and there will be extension in this string due to this weight mg, and hence also in the equilibrium condition, or every time on the motion, we shall discuss later. So we'll talk in the equilibrium state. We'll see that due to this W, there will be a tension produced in this string. We call it light string because we are not going to consider here the weight of this string. All right. And in the beginning, suppose that its length was means original length. It is in fact original length we are talking of. Original length of that light string was, for example, L. Then due to this weight of this body, its extended length has gone up to here, and this length we can suppose as delta L. So in this case, we can say that T is directly proportional to the extension, that is delta L, according to Hooke's law. So you can see that in general, we define Hooke's law as follow: tension in an elastic string, which is supposed to be light. That means we don't consider the weight here, produced by a deforming force is, deforming force means the external force. For example, here this is W, is directly proportional to the extension in the string within the elastic limit. What does elastic limit? It corresponds to the maximum extension after which the material either breaks or starts to show plastic nature. A plastic body is the body which doesn't regain its shape when the deforming force is removed. And in opposite to that, in an elastic body, you can say that when you remove the deforming force after being extending or compressing the object, it will regain its original shape. So let's come back to this proportionality relation. And after that, you can write T equals to K times of delta L, where K is a constant of proportionality to be determined. So in order to determine K, let's first discuss about modulus of elasticity lambda, also called Young's modulus. So lambda is defined as the ratio of stress by strain. And you know that, or you should know that stress is a kind of pressure. So this is defined, stress is defined as force per unit area, and the strain is defined as change in length by original length of that material in elasticity. Okay. So after that, what you can get here, like F by A equals to, if you transpose this to the left, then it will be lambda times delta L by L, or you can also write lambda by L delta L like this. And if you talk about the unit of lambda, you can see that here in this case, force, SI unit for force is Newton, and then for area is a square meter. So this is Newton per square meter. And here to the denominator, you can see that unit for one length is meter, SI unit is meter, and another length has also the same unit. So these two units will cancel each other. Therefore, unit of lambda is Newton per square meter. And for F by A, you can say that this is the force responsible to produce tension or thrust in the material. For example, tension in the case of you extend the body, and the thrust in the case of you compress the elastic body. So here, if you compare this sort of relation with T equals to K delta L, we see T is produced due to force F applied to the material to deform it within the elastic limit. Therefore, in F by A, we write F by 1 square meter, means we keep cross-sectional area as a unit, and that will be now F only, which causes the tension to produce in the elastic body, or thrust to produce in an elastic body, and therefore lambda can now be expressed in Newton. Hence, T equals to lambda by L delta L. But throughout this chapter, we use X for delta L to denote the extension. So we can write here T equals to lambda by L times X instead of writing delta X. Note that lambda depends on strengths of materials. Therefore, it is different for different materials, but same for a particular material. Therefore, lambda by L can be taken as a constant. K you can say, and we have used K for a particular material or particular material of a body. Let's now discuss the graph of lambda for a particular material, for example. So you can see that lambda equals to a stress by strain, and by cross multiplication, you can see that stress equals to lambda times strain. You can see here for a particular material, lambda is constant, and stress and strain both are variable. So strain depends on stress. So if you plot a graph, then your graph looks like that within the elastic limit. So up to here, you can say that this is the elastic limit, and where you can see that after this, when you keep on applying the stress or the tension in this string, then either the string or the material breaks at this point, or it starts to show the plastic nature. So this sort of graph part is for plastic nature of the body. All right. So here you can say that the extension is 0, and as you increase the stress, the strain will also increase, and the same thing you can see obviously from this graph of T equal to Kx. This is also a graph of a straight line. You can see here where extension depends on the value of tension over there, and K is a constant quantity that we have already seen. So here in this case, up to here, the material has the original length, and about this, as you increase the value of tension, the extension will also increases according to Hooke's law, and it will show you that the direct relation between T and X up to here, which is called the elastic limit. This is the elastic limit point. So what happens after that, if you further increase the tension or further extend the spring, for example, or a string, for example, then either that string breaks at this point called elastic limit, or it starts to show the plastic nature. And then what happens after that, if you further increase the force, then what happens? The extension, there will be increase in extension. All right. But even if you decrease the force, that means it is going down, T value is going down here, but still extension will increase. You can see that from here to here, the value of T has been decreased, but still X is running horizontally over here. So in that case, it is still increasing. So up to the elastic limit, if you remove the deforming force, for example, T over here, it will regain the shape to 0. But when it crosses the elastic limit, it will either break or it will start showing the plastic nature. So Hooke's law is defined within the elastic limit. So let's now generalize the Hooke's law. Is that simply you can say that in general, tension in the inner or in an elastic string that we talk about here, light elastic string, that means weight of the string should not be considered here. So tension in an elastic string is directly proportional to the extension. That means extension in the spring depends on the tension produced due to the applied force, due to the external force in that material. The extension in the body within the elastic limit. That means we have T is proportional to X, where X is the extension in the string, and after that T equals to Kx, where K is the constant of proportionality, and we replace K by lambda by Lx, and here lambda is the modulus of elasticity. This is different for different material, but for a particular material, lambda is constant, and L is the original length, and X is the extension. And if you say that, if you want to say that what is the extended length is in fact the sum of original length and the extension. All right. And here, if you talk about, again, the unit of T is Newton, and also the unit of lambda is Newton, and these two lengths are expressed in meter if you are using SI, unit of measurement. So let's now discuss a problem where the Hooke's law is applicable. So here the problem states that a light string, that means we don't consider the weight of the string. A light string of unknown natural length is fixed to a ceiling at one end with a mass of 0.4 kg attached to the other end. The string is allowed to hang in equilibrium such that the length of the string is now 15 centimeter. That means the extended length is 15 centimeter. If the modulus of elasticity for that material is 20 Newton, find the natural length of the string. So in order to solve this problem, where here you can see that Hooke's law is applicable. So let's see that how we apply Hooke's law in order to solve this kind of problem. So here you can see that this is a light string of original length is given as L equals to, we don't know. All right. So this is unknown length up to here. And this is a particle or a body whose mass is given as, you can see here that this is 0.4 kg. All right. And due to the gravity, there will be weight for this body, and this weight is given by W equals to mg, and your m value is here 0.4, and times g value is 10. We take acceleration due to gravity as roughly 10, so it is now 40 Newton. All right. So no, it is 0.4, so it is now 4 Newton. Okay. And due to this weight, there will be a tension produced in this string in the opposite direction, and in this situation you can see that the body is in equilibrium state. All right, so in this case L is given that, but you know that up to from here to here this length is x, but the question says that the string is allowed to hang in equilibrium such that the length of the string is now 15 centimeter. That means after extension the total length of the string is now, it is L plus x, in fact, from here up to here, and that value is given as now 15 centimeter. And if you are using SI unit of system, then you can write, you can convert that in meters, which is 0.15. Otherwise, no problem here. You can just leave it in centimeter. Okay. So now it is asking you to find the natural length of the string. So here you can see that this is an elastic body, and it has been extended to the length L plus x due to the force W, which is weight of this body in equilibrium state within the elastic limit. Therefore, Hooke's law is applicable here. So by Hooke's law, we know that T equals to lambda by L and times x. And your T value is here. The T value is given as, it is not given as, it is found as the value of W equals to 4 Newton. And lambda is given as, you can see here the modulus of elasticity is given as 20 Newton. So you can use 20 Newton for lambda. And L plus x is given as, it is 0.15 meter. And then if you'd like to express x in terms of L, then x is equal to 1.5 minus L. So therefore you can write T equals to lambda by L by x. So you put all these values. So T value is 4 and lambda value is 20. And L value we don't know, we have to find it. And this is 0.15 minus L. Now you solve it. We here 3 divided by 24, and then take a calculator. In your calculator, you will see that this value is 0.125 meter, and this is the answer. And for example, it's not given here, but if you are asked to find the value of x, for example, so you have here L plus x equals to 0.15, and then you can find x equals to here 0.15 minus the value of L, the original length. The value of L is, this is 0.15, and the value of L, we have just now got it, 0.125. So take your calculator. In your calculator, you'll see that this value as, this is 15, this value as 0.025 meter. So this is possible that you can either express your answer in terms of centimeter or meter. It doesn't matter here, but all those units are in the SI system of the unit. Therefore, this is good to take the unit of other dimension also in terms of SI unit. So this is good idea to convert the given centimeter into meter. For the further details of problem solving, I have solved some of the related problems from the exercise on Hooke's law, which you can find in the description box. So in the description box, I'll put the link over there, and you can click on the link if you want to access some other kind of problems that make use of Hooke's law. So guys, this is all for now, and thank you for your patience.
hope you all enjoy watching this class lesson, and please subscribe to this channel and don't forget to like and share this video. Thank you.